Yeah, so last time we have discussed abelian extensions obtained by adjoining roots of unity, and there are some exercises in the Google class that generalize this slightly. So today we are going to discuss another source of abelian extensions in the case when there are sufficiently many roots of unity. So abelian extensions of those fields that have many roots of unity. So, well, this is also called the Kummer's theory. Okay, so so the setting is as follows. So let we consider some well, as usual, we can start from a sufficiently big field, or we can start with a smaller field. So suppose let K be a field, and we assume that it contains a primitive nth root of unity, nth root of unity, in particular, this means that n is not divisible by the characteristic of K. So let L be a Galua extension.
Excuse me, in what sense is the root of unity primitive?
It means that this means that it is a solution of the equation x to the n is equal to 1, but which is not a solution of the equation x to the m equals to 1 for any m strictly smaller than n. Yeah. Oh, sorry. Yeah. So you see, it is nth root of unity, but it is not a root of unity of smaller order.
Thank you.
So yeah, so we consider a Galua extension. So with a group with group G. So this means that K is the fixed field of the group G. And so we are looking for the maximal abelian extension of our field K inside L. So just to set the notation, so the maximal, so maybe it's not a completely definition, it's a claim, yeah, so maybe an exercise or whatever. So maybe so claim that there is a subfield of L containing all abelian abelian extensions of K, extensions of K inside L. Yeah, so namely, well, essentially it is it's quite trivial, but let me I'm afraid that we haven't discussed this in detail, but this is a corollary of the following lemma, which we had to consider as a part of the Galua correspondence. Yeah, so this is a consequence of the following lemma. So if so let L G be well, so again, this is a Galua extension. And then the Galua correspondence transforms then the Galua correspondence transforms compositor. So what can we have? We have subgroups, yeah. So suppose that H1 and H2 are two subgroups. So what can we form with the two subgroups? With two subgroups, we can form their intersection, and we can form the smallest subgroup containing both of them. So this is a subgroup. The subgroup generated by the subgroup generated by them. Actually, we don't. We can consider an arbitrary collection. Yes, so maybe even not of two, but by several subgroups. So.
Excuse me.
Yes.
Also, the lemma is the Galua correspondence and transforms H1 intersect H2, and then
Yeah. So we want to say that actually the compositor of subfields correspond to intersections of subgroups, and the subgroups generated by certain subgroups correspond to intersections of subfields. So this is let me write this, that intersection is transformed to the compositum of the fixed field, and this subgroup generated by several subgroups corresponds to the intersection LH1 intersected with LH2. Yeah. And the proof is actually evident because so let us because actually what is so the proof So the proof. So what let us call this simply H. H goes to what? To L of H, and this means that it consists of elements fixed both by H1 and H2, and this is precisely LH1 intersected with LH2, so this is trivial. And concerning this composition, the first error, you can ask what is so under the converse Галуа correspondence. Let us look where do the compositor go. So so for instance, if we have K, so F1, F2, and so on, intermediate subfields, subfields in our Галуа extension. Then the compositum goes to the automorphisms of L over this compositum, and this means that it consists of all elements of the Галуа group identical on one of these subfields and identical on the another one. So this is for trivial reasons, this is just an intersection of F1 intersected with G L F2. And this is precisely what we want to have here. So this is H1 intersected with H2. So this is this is trivial modulo the Галуа correspondence. Okay, and so what does this mean? So how could we? So what do we want to conclude? We want to conclude that a compositum of abelian extensions is abelian itself. And so why? Because what does it mean that so proof? So suppose that well, we have this fi over k is abelian, means that what does this mean, that this is abelian? This means that the quotient of our group, over the whole Галуа group, by
Excuse me, a composition of abelian extensions.
Compositum.
And compositum is what?
Композит.
Если честно, лучше не стало.
Можете,
пожалуйста, просто напомнить быстро?
So the compositum, so definition, so given a field extension L over K, and sorry, given a field L, given a field L, and a collection and certain subfields K1 and so on, K2. The compositum of sorry. The compositum of all these subfields is the minimal field containing all of them is the minimal subfield of L containing all of them. Containing them. Okay.
Okay, thanks.
So now, what does it mean that a certain extension is abelian? It means that the Galois group of Fi over K is abelian. What is this group? This group actually this is the quotient of the whole Galois group. So you have a surjection of the big Galois group of the field L. You have a surjection of this Galois group on the Galois group of each of Fi's, and the kernel is the subgroup of those automorphisms of L that act identically on Fi. Yeah? So what can we say about the Galois group of the compositum? Yeah. So by this lemma, we know that the Galois group of the compositum, so the Galois group of the compositum F1, F2, and so on, over K is the quotient of GL over K by the Galois group. By the Galois group over the compositum. What is this? And this is just the intersection. Yeah. So this is the same by the lemma. It is the quotient by K of GL. K F1 1K L F2 and so on. And you see that actually this is what is this? What is the intersection? The intersection is just the kernel. So you can consider the move from G to the product, or to the product of G of L over K modulo G. Let me write this product. L over Fi, yeah, and so this is abelian because our extension is abelian, yeah. So this is abelian. So the product is also abelian, and and this is actually an embedding, and this is surjection. Yeah, so you see that our group is embedded into an abelian group, and therefore it is embedded. It is abelian itself. F2 is abelian over K. Okay, so and this means that the notion of the maximal abelian is well defined. So maximal abelian extension or sub-extension. Yeah. So I have not. Yeah. So in this claim, yeah. So you see that there is maybe I should write this here. There is a subfield of L containing all abelian extensions of K and L, which is called the maximal abelian extension of K in L. Sometimes one can talk about the maximal abelian extension without explicitly mentioning L, but this simply means that you deal with certain sufficiently big extension, like an algebraic closure or something like this. Sorry, not algebraic, but separable closure. Yeah. Okay, so then we remove this.
Excuse me, how would, well, in this corollary, how did we get that GL over K to G F1, F2, and so on over K is an embedding?
Because you see the kernel of this map, of this map phi is the intersection. You see that the kernel of this. So let me write this. The kernel of phi is the intersection of this G L over Fi. Yeah. And this is the Galois group of L over the compositum. Okay, and this is so, and our Galois group, which is encircled in blue, it is precisely the quotient of the Galois group of L over K by this kernel.
Okay. And then why is the not the embedding well, the second arrow from GF F1 F2 to the
This one.
product. Yeah, this one.
Yeah, this one, because you see that this group is precisely the quotient of this by the kernel of phi. So this is surjection.
Okay.
And its kernel, the kernel of this. Let me write this. Let me just call this maybe pi, just projection. And the claim is that the kernel of pi coincides with the kernel of phi. So the kernel of phi is the intersection. The kernel of pi is this Galois group.
Okay.
Maybe let me write this on the right. Yeah. So this is the kernel of pi. So this is by definition. By definition, this is the kernel of pi, and this is by definition, well, almost by definition, this intersection. Okay.
Okay, thanks.
Now, now I want to write certain, coming back to our setting. Now we assume that our base field contains a primitive nth root of unity. Okay, and let me write the following map. So we take yeah. So we consider. So and we have fixed. So we have fixed some n. So n is an integer. So n, maybe n equal to 1 is not that interesting, but just an integer. So we consider the following. We consider the intersection of our base field and the group of nth powers. So this is nth powers of elements of L. Of elements of L. Yeah. And now we want to construct a map. So let me denote. So denote by mu n the group of nth roots of unity. And let us define the following map from this group. You see that this is a group, of course. If you wish, you can let me write this. Well, it doesn't matter. Yes, it does matter. It does matter because we don't want to consider zero. We want this to be a group. So we consider morphism to the homomorphisms from the Галуа group to mu n. And of course, you see that mu n is actually a cyclic group of order n, because we assume that our field K contains a primitive nth root. So now what is this map? We take an element here and then we associate to each element of the group G the following ratio. We act by the element G.
And is this CG or what? What is this? What's written near the G? Yeah.
This is just a bracket.
Okay.
It's just a bracket
So
because
okay, it's a map. Okay, thanks.
you see we have to write down a homomorphism which sends each element of the group to some root of unity. Okay.
All right then.
Yeah. So what do? We just take nth root of f. It is well defined. So nth root of f is well defined. The modulo is well defined. Modulo a root of unity, yeah, mu n, and then divided by the same nth root of f. And you see that this is well defined because if we choose another root of f, then it will differ by a multiple here. But this is an element of k, yeah, by our assumption. So the G action on this root of unity is trivial, yeah. So and this.
Excuse me, and what's the idea of this action? Maybe then we send G to the nth root of G or something
No,
like
G
that.
is an element of big G. If you don't
Yeah.
like,
So
we
and
want we want to send it to a root of unity.
and are you sure the thing on the right is the root of unity?
Yeah, because if you raise it to the nth power, then you get G of f over f, and f is an element of k. So this is an element of k. So it is fixed by G.
Mm-hmm. And the G is still a Galois group.
Yes, G
Okay.
is the Galois group of.
And it's so it's uh okay, and I think I understood. So after G there should be brackets, or not?
No, the second bracket is here.
No. The brackets. It's
You mean this here?
yeah. Just
Oh.
can't explain this in
Mhm.
English. Sorry.
Okay. Mhm. Okay. Yeah. So let's see. What is the kernel of this map? So the kernel consists of those f uh, uh, such that nth root of f belongs to k. Yeah. So those f that that square nth root of f belongs to k. Yeah. And therefore this simply means that it is nth powers of elements of k. Yeah. So and the conclusion is that uh, we get an injection of the following group of this group modulo the nth powers of elements of k into homomorphisms from G to mu n. Okay. Now we want to check the subjectivity. So how about subjectivity? Yeah. Yeah. So first of all, let us let yeah. So subjectivity. Yeah. So let phi be a homomorphism. Phi from G to mu n be a homomorphism. Then what we are going to do, we are going to construct a certain semilinear representation, yeah? Namely, then okay, yeah. So consider the following the following the one-dimensional semilinear representation, one-dimensional semilinear representation of G over L. Maybe the following.
Excuse me. Consider the one-dimensional semilinear.
One-dimensional semilinear representation. So to define a semilinear representation, we just have to define its action on some. It is one-dimensional. So we just have to fix certain vector with a vector E, some non-zero vector. We just have to define its action on this vector. Yeah. So we say that G x on E by multiplying by this by the value of this homomorphism. Yeah. So by definition we can assume that our representation, our group acts on this vector by multiplying by the value of phi. Okay, and but we know that that all representations, similarly representations, are trivial, but this representation is trivial because our group is finite. Have we assumed this, by the way? No, we have not, but yeah, we should assume that this is a finite. Maybe, yeah, maybe we discuss the case of arbitrary Galois extension. We will discuss later because, or maybe even today. But so just assume that it is finite. Assume this for simplicity, but it's not very important. But if it is not, then we have to say a little bit more about this homomorphism phi. Yeah. So, but this representation is trivial. Is trivial in that sense that there is a vector, a non-trivial vector fixed by the whole group. That is, there is a vector fixed by this group, and this means that all vectors are multiples of our E. So there is an element F in L such that Fe is fixed by G. Yeah, so it is fixed by G. This means that G of Fe is equal to Fe for all elements of our group, of our Galois group. Now, what is written here? Here we have F to the G times phi of G times E. Yeah, so yeah, all right. So this means that phi of G is equal to well, maybe maybe it's, well, it doesn't matter. Yeah. So this means that f phi of G is f over f to the G. Yeah. But now let's yeah, maybe it's not a good. It was not a good idea to use the same letter. Maybe let me put here H. H. Yeah, here. H, and H here. H. Right. Now, but we know that actually this is a root of unity, nth root of unity. So H to the n. Yeah, maybe I should write for all G. And H to the n is equal to the H to the n G. Yeah, again for all G, and this means that H to the n actually belongs to the field K. All right. So And this actually means that if so phi of g is equal to what? To g of nth root of h to the minus n, and let me remark that h minus n is also an element of k, over nth root to the h to the minus n. Yeah, and therefore our map is actually surjective. Yeah. So then the conclusion is well, it's Kummer isomorphism of Kummer's theory. That our map, what here we have already transformed it to an injection, but now we can say that actually this intersection modulo n powers of the elements of K is actually isomorphic to homomorphisms from G to Mn. Here, well, once again, here we assume that all that the primitive that K contains primitive roots of unity, assuming mu n is contained in L, sorry, in K, and also that it is of order n. Okay, and yeah, and now we want to construct to make this Galois correspondence explicit. So, and actually we have already constructed these.
Excuse me.
Yeah.
First, we got that this map is injective, and then
Yeah.
we have just proven that it's surjective.
Yes.
Thanks.
Yes, and the maximal maximal abelian extension of K is sorry, K in L is the compositum of yeah, maybe I should not say that it is a maximal. Yeah, maybe I should say and yeah, maybe I should state it as a Galois correspondence. Yeah, maybe not maximal, but and there is a correspondence. There is one-to-one correspondence between subgroups of this of the source of this isomorphism, K bisected with L to the n over K to the n. Sorry. And abelian extensions. Of K in L, and the correspondence is given as follows. For instance, so for instance, starting from a subgroup here, H, you send it to the compositum. Compositum of K of nth root of x, where x modulo this nth powers of k belongs to H. Okay. In particular, so this is in particular, you to get the maximal abelian extension, you have to take the whole H. So you take all nth powers of elements of L that belong to K, and you adjoin to K nth roots of these elements. So this is the Kummer theorem. Okay, now you might ask what. So you see, we cannot get this way certain abelian extensions here, even if our base field K is big enough, so it's even if it contains all possible roots of unity, it may happen that there are, for instance, no primitive roots of order P, where P is the characteristic of our field. So there are other, there may exist other abelian extensions that don't come from Kummer theory, namely what they are called Artin-Schreier extensions. So other but you see that if n is not divisible by the characteristic, then of course we can get all extensions of period n this way. So so you see that this group is annihilated. So remark this way. We get some extensions, some abelian extensions of period of period n, in the sense that the group is annihilated by multiplication by n. So other example is given by so maybe I should write it, the Artin-Schreier extension, Artin-Schreier extension So what was essential here in this construction? That we actually try to describe the homomorphisms from the Galua group to a certain cyclic group, and this does not work in the case when when our n is divisible by the characteristics. So so it is. Let us pose the question: what could be the extensions of a field of characteristic P? So let K be a field of characteristic P, which is of course positive, and we want to construct an extension of K with a Галуа extension with the Галуа group isomorphic to, well, some with the Галуа with the cyclic Галуа group of order P. Yeah, so this is sorry, what's wrong here? Oh, I'm sorry, I lost the page. It's here. Suppose, yeah, and maybe we can fix some alpha in K, and suppose that x to the p minus x minus alpha is irreducible. Then I claim that that adjoining root of this polynomial gives an extension which is Галуа, and with the Галуа group isomorphic to the residues modulo P. Yeah, so then L, which is just the field where we obtain by adjoining the root of this polynomial, is a Галуа extension. Is a Галуa extension of K with the Галуа group isomorphic to the field of P elements. Yeah. You may ask why. Well, it's actually it's clear because the proof is rather evident, because you have an automorphism which of this L gives an automorphism of L.
And what's the statement that we're proving right now? So
yeah, this one, that that this extension is Галуа, and its Галуа group is cyclic of yeah. So this is an automorphism, and of course its order is P. Yeah, so if you because so this is okay. So all right. So this gives another source of examples, but we can. You see that so far we only get extensions that are. You see that of course we can take several. Yeah. So maybe I should formulate some kind of correspondences, Галуа correspondence like here. Yeah. So it's here we had a correspondence between certain subgroups and abelian extensions of order of this kind of extension. So let me state this way. So denote by P a map from K to itself, given by sending any element alpha, sorry, maybe not alpha, some beta to beta to the P minus beta, and then there is there is a one-to-one correspondence between here again between here we assume that, of course, that the characteristic is positive and equal to P. There is one-to-one correspondence between subgroups of the quotient. So in the case of Kummer theory, the quotients are modular nth powers of the elements of K. But here we consider the quotients of K as the additive group of K modulo the image of this map P of K. And
excuse me, how did we call this map?
P.
P, okay.
Yeah, and Galois extensions cyclic. Well, I should say cyclic extensions of K of period P. Sorry, not cyclic. I'm sorry. Abelian extensions. Abelian extensions of K of period P. Abelian. Okay, so well, you just
and the period of an extension is
it's a period of its Galois group. It
okay.
means that
Okay, there's just the period of the group. Okay, thanks.
yes, the group is annihilated by multiplication by P. Okay, yeah. So and the correspondence looks as before. So you just take a subgroup and adjoin. So K of so you take the pre-image and the P of all elements. So you just consider you just add all solutions of this. Yeah. So you take P of alpha, all P of alpha, where alpha modulo P of H, sorry, P of K belongs to H. So this is you might say that this is less explicit than Kummer correspondence, but you see that actually there is no much difference whether you use nth root of unity or you use this p inverse. Yeah, actually this is also just some single function, and as well as this square root of nth root of nth root function. Yeah. Okay. Yeah. Maybe. Before, yeah, so you might ask what can we do if we want to consider extensions of period, say p square. What if we want period some other power of p square, p cube? Well, then we have to consider. Then we have to consider. Yeah, maybe to prove this. So you see that so far we. We have not proved this. Yeah. So to prove this, we have to. Yeah, maybe we will discuss this later. I just want to announce that this is to deal with higher degrees of p. We need to introduce with vectors. But we will do this later. But let us come back to our abelian extensions of period p. So how did we prove that this is actually a one-to-one correspondence in the case of Kummer theory? Well, you see that actually our here we just use Galua theory because so what are abelian extensions? Abelian extensions are those they correspond to certain subgroups of G, such that the quotient by this subgroup is abelian. Yeah, and in the case of so essentially what we want to do, we want to know what are homomorphisms from G to abelian groups, and to do of abelian groups of period n. Yeah, if we deal with abelian extent. Sorry. Yeah, I'm sorry, I forgot to write this here. Abelian extensions of period n. Yeah. Yes. So yes, and any abelian extension of period n corresponds to a certain subgroup of G, such that the quotient is by this subgroup is of period n, and of course all such subgroups are captured by these homomorphisms to the mu n, which is a cyclic subgroup of order n. Yeah, so we need some kind of so what we need to prove that yeah, so proof consists of constructing an isomorphism, constructing an isomorphism isomorphism. From this quotient k of k, two homomorphisms from yeah, so here I want to write G. Wait, I'm sorry. G. I skip this. Just a second. I will explain what is this G. To FP. Yeah. So now what is G and what is now I am forced to explain what is this home and what is this G. So what is this G? You see that in this case we are forced to admit sorry. Yeah. So here. Yes, so in this case we are forced to admit infinite extensions. So actually what can we do? We can assume that, let me write this, that where G is just what is called absolute Galua group. This is a Galua group of the separable closure of k over k, and homomorphisms are understood as continuous homomorphisms, and hom is understood as continuous homomorphisms. And continuous actually means that they have open kernels with open kernels. So actually this means that all such homomorphisms that we consider here factor through certain finite quotients. So G, in other words, for any such homomorphism phi, so for any such phi, there exists a finite Galua extension, L in this separable closure, such that phi vanishes on the subgroup of the absolute Galua group, which is identical, acting identically on this infinite extension. Okay, so yeah, and now how can you construct this isomorphism? Of course, there is a map as usual. The map constructed is precisely the same way as before. You just map your element.
Excuse me, such that phi from of that extension is just this G of k sap over L is in kernel of
Zero.
phi.
Zero. Yeah, you see
Zero,
that?
okay,
Yeah,
okay.
yes, in the kernel of phi. Yes. Yeah, you can write this way. Yeah, so that. Yeah, so this. Yeah, you can say that this is yeah in the kernel of phi. All right. Yeah. So how do you proceed here? Yeah. So you can. So you start with. Well, you proceed the same way as before. So you. But here, instead of you see that there we considered quotient, a quotient of this of the image of some element under the group element by the element itself. Not here. Sorry, it was here. Yeah. So here we considered the quotient, but now we consider difference because everything is additive. So we take the pre-image. So the pre-image of f. Of course, it is not well defined. It is defined modulo. So it is well defined. Well defined modulo modulo fp. Yeah. Modulo some element of, you can add some element of the prime subfield, and then subtract. Sorry, you have to act on it by G. Sorry. This is again. This is again a homomorphism minus pi minus inverse of f. Yeah, and actually this is a homomorphism. By the way, we have not checked this, that this is a homomorphism in the multiplicative case, but it is quite. This is an exercise. I mean, it's very easy because it's easy to check that this is a homomorphism from G to Fp. Yeah, and of course its kernel coincides with those. So the kernel it coincides. It is the set of those f that they are pre-images. So this is f and k. Those that their pre-images are fixed by the group G. Yeah, so it is fixed by the group G, and this means that they belong to K. So this simply means that it is the set of. This is simply the image of K. Yeah, and therefore the quotient of K by P of K embeds into this. Into the group of homomorphisms from G to our prime subfield. Okay, now to prove, yeah. So for subjectivity, we actually need something which is sometimes called additive Hilbert theorem 90. It's not completely what we really have already discussed. So maybe may I ask you a question? Who knows what cohomology of groups are? No? Did you hear something about group cohomology? No?
I have heard the word, but I don't know what it means.
Okay. Maybe I can mention. You see that what I actually when discussing semilinear representations, what I was trying to do is to avoid group cohomology, and actually we succeeded this in the multiplicative case, but in the case of yeah, so here we can also try to avoid them, but mm, yeah, but maybe well, well, let me just um, uh, we don't have too much time. Maybe I'll postpone. So postpone subjectivity. Postpone the subjectivity. Um, and maybe maybe we could. So we have two options. We can, as we started to deal with infinite Galois extensions, we can either discuss the infinite Galois correspondence, or we can consider, yeah, maybe we don't have much time, so maybe I'll just give you some funny example of you see that we here we have encountered this absolute Galois group, so maybe not this one, but to make it uh, to make it yeah, so it's here. You see that here we started to deal with absolute Galois group, and you may ask what can you say about this big huge group? So maybe not that big and huge. Of course, this is again Artin-Shire. It's a funny thing that again this is again Artin-Shire theory, but something else. Yeah, so absolute Galois groups. Of course, you definitely know that that some Galois groups need not be too huge. Yeah, for instance, you probably know that the Galois group of the complex numbers over the real numbers is not that big. Yeah, it is simply the group of two elements. And so you may ask, maybe there are there are some cases where this Galois group can be, say, of 3 elements or 4 elements, and the answer is no. That this group is always, if it is finite, that is it consists of at most 2 elements. Yes, so let us prove the following fact. So it is due to, again, to Artin and Shire. And so but actually we don't need our big field to be like see here. Need not to assume that it is algebraically closed, but we want that it has no non-trivial abelian extensions. And as you just saw, the abelian, it's easy to construct abelian extensions, because you see that we actually know how to do this. We just we know how to we can add all roots of unity So maybe I should write this. Yeah, maybe. Well, we haven't actually finished with this surjectivity, so I cannot say that we have proved all this, but in principle we know that how to construct abelian extensions. You just add all roots of unity. You can consider all Kummer extensions, yes, by using roots roots of elements that we have already constructed. And if our characteristic is positive, then we have to add all preimages of Artin-Schreier maps, yeah, and also and then we just iterate this this procedure, and thus we at least theoretically we know how to construct all abelian extensions. So that's not very difficult. And so now we assume that there are no abelian extensions. So let F be a field with no abelian extensions. Field with no abelian with no abelian non-trivial extensions, of course. Extensions. Well, for instance, we may assume that this is separably closed, and H be a group of its automorphisms. And H be a group of its automorphisms. You see, we do not assume that H is finite, but what we do assume, we assume that each element of H is a finite order. Each element of H is of finite order, and then in this case H is of order at most 2. This is the first part, and the second part says what happens if this group is of order 2. So if K is a proper subfield of F, over which F is finite, over which F is finite. So you see, we don't assume that this is a Galois extension, that K is a Galois extension of F. Then K is totally ordered. K is totally ordered, and F is just quadratic extension of K obtained by adjoining the square root of -1. Okay, so and so it is non-trivial, yeah. So it is non-trivial. So it is so is a Galois extension. Is Galois, of course, is Galois over k, and of course it is of degree 2. Yeah, and in particular, this means that the characteristic it follows from this condition that k is totally ordered, that the characteristic of f is 0. Okay. All right. So yeah. The proof is quite non-trivial in the sense that we have to consider many cases. Yeah. So first of all, f should contain all roots of unity, as we discussed, because if we add a root of unity, then it will give you a non-trivial abelian extension, but we assume that there are no such abelian extensions, so it should contain all roots of unity. Okay. Next. Next, it of course it contains if it contains an element W, and n is not divisible by the characteristic, then f contains nth root of W. Yeah, because otherwise it is an abelian extension. Okay. So of course we may assume that H is non-trivial. Assume H is non-trivial, and it contains an element sigma, and we may assume that it is so this is non-trivial, and we assume that pth power is 1 for some prime p. Yeah, for prime p. Okay. So what we want to check that this prime is not the characteristic of p. Sorry, in the characteristic of f. Because if p is the characteristic of f, then we have we have the following yeah, so we can consider the following Galua extension. Sorry, so this is let us call this K. Let's call this K. So we know that then then this well, again, we unfortunately we have to assume that this is Artin-Schreier extension. Yeah, so then yeah, so we can say this. So this is then we set k equal to the fixed field of f. Now so f is obtained by adjoining root of Kummer equation. Alpha to the p minus alpha is a and k. Well, for some a for some a in k. Right. So now we want to get a contradiction. Yeah. So any element of f can be presented uniquely in the following way. It will be a linear combination of powers of this alpha with coefficients in k. So it will be I alpha to the I, where bi are elements of k. Yeah, now let's apply this Artin-Schreier map to B. Then we get b to the p minus b is equal to what? It's equal, so when we raise this to the p's power, we get just sum of p's powers, bi to the p alpha ip minus bi alpha I. Okay, so now what is yeah, so what is alpha to the p? Alpha to the p is alpha plus a. So this is equal to sum from 0 to p minus 1 pi p of alpha plus a to the I minus bi alpha I. Okay, and yeah, so yeah, so now if we consider this modular lower degrees of alpha, so we get only, so consider only I equals to p minus 1. So this will be so the b to the b number p minus 1 to the p minus b p minus 1 to the b minus 1, yeah, alpha p minus 1 modulo k yeah, modulo k linear combinations of 1 alpha and so on alpha p minus 2. Okay. All right. So But what would this mean? This means so there are. What do we know? We know that there are no there are no Galois extensions of f. Yeah, there are no extensions of Galois of f with well, cyclic extensions of f of period.
Excuse me, there are no
Cyclic. There are no cyclic extensions of f of period p. Yeah. What does this mean? This means that this yeah. So yeah. This means that, for instance, if we take equation x to the p minus x equals to a alpha p minus 1, then it has a solution b, yeah, b in f. Okay, and therefore so when we take such a b here, so you see that it is b to the p minus b is congruent to this modular lower degree terms, yeah, and this means that b to the p minus 1 p minus b to the p minus 1 is equal to a for some element already in K. Yeah, but this is contradiction because we know that alpha is not in K because it is it gives a non-trivial extension. So this is contradiction. Yeah. So this means that if there is an element of I'm sorry, yeah, so if there is an element of prime order p, then p is not a characteristic. Yeah, so now sigma to the p is 1, sigma is not 1, and prime p we exclude yeah, so now we exclude the p equal to 1, so we consider only negative primes and assume that they are not equal to the characteristic of f. Okay. All right. So then again, it is a cyclic group of prime order, so there are no intermediate subfields. Yes. So there are no intermediate subfields. Let us consider, again, we assume that all roots are there, yeah? We have already. Yeah, so all roots of unity are there. Yeah. But we want to say that yeah, so all maybe not all, but well, yeah, it is not characteristic. So all pith roots of unity belong to the fixed subfield. Okay. Because you see that if they are not there, then otherwise otherwise the abelian extension otherwise you see that there are no intermediate subfields. So we know that they are all pith roots of unity are in F. So F sigma of mu p is in F, but the degree of this extension is less than or equal to p minus 1, but sorry, F sigma, but here the degree is p, yeah, so it's not possible, so because all degrees should be divisors of p, so and yeah, so this is contradiction. So yeah, so we assume that all pith roots are there. Next, okay, next so we can apply Kummer theory. So then F, so Kummer, then F is obtained by adjoining certain nth root of some element. Sorry, not nth, pith. Let me denote this root by x, and so x to the p belongs to the fixed subfield, and therefore, so let us look at the action of the of sigma on x. You see that it is fixed by sigma, and therefore sigma x is just the same x, but times certain root of unity, which is of course this root is not trivial, and it is a primitive. Yeah, so it is a primitive pith roots of unity. All right, so. So now we can fix. You see that we continue this process. So we look at you see, as we don't have any abelian extension, we can there is a piece roots of x in f, so we can fix we can fix some nth roots of x in f, which we call y, such that y to the p is x, and then what happens with y if we act on it by sigma? So x y sigma is now psi times y, where what is psi? Psi, we don't know what is psi. It is of course certain root of unity, but psi to the p is our zeta, yeah, because if raised to the pth power this equality, then we get this equality, yeah. So this is why this is the root of order p square. It's of course primitive. All right. Right. So.
Excuse me, where psi pth equals what?
Psi to the p. You see, if we raise this. If we raise this, you see that you can understand this formula is that psi is something. You just divide y to sigma by y, and you get psi. But if you raise this to the pth power, then you get x to sigma equals to psi to the p times y, times x. And if you look here, you get that psi to the p is zeta. Okay, so psi is also a root of unity. So yeah, and as we know, roots of unity give abelian extensions. So what is yeah? So yeah, okay. So they are in. This is an well. Don't sorry. Never mind. We don't need this because we already know that sigma is well defined. Okay. So yeah. Now we want to. Now we want to understand the action of sigma on psi. Yeah, so let's write that sigma acts on psi by what is psi? Psi is a primitive root. Yeah, so any image of primitive root is again a primitive root. Yeah, so it is a xeta. It is a psi to b, where b is some invertible residue modulo p square. Yeah, because this is root. This is a primitive root of order p square. Okay, then coming back to y. So we act on y by sigma p times. So what do we get? When we act on the first time, this y is multiplied by psi. When we act the second time, it is again multiplied by psi and multiplied by psi sigma, and so on. It is multiplied by psi to the sigma to the power p minus 1. And so we can rewrite this as xi. Now we replace sigma by b, yeah, because so we get this 1 plus b plus so on plus b to the p minus 1. So this is a geometric series. Okay, now we want to say that actually b is so let's come back to this come back to where was it? I'm sorry, I lost it. It's written here that zeta, yeah, so this means that zeta belongs to zeta is fixed by sigma, yeah, have sigma, and this this implies that b is congruent to 1 modulo p.
And why is that?
Sorry?
Why is b
This implication?
yeah.
Because you see that if we raise this to the pth power, we get zeta to sigma equals to zeta to b, and zeta is fixed by sigma, so this is simply zeta. So zeta to the b is zeta. You see that this means that beta is 1 modulo p. Okay, yeah. Now, what can we see here? This, yeah. So, and therefore, this geometric sequence, geometric series, is congruent to p modulo p square. You can write this. This is an exercise. You write that b equals to 1 plus p, say t, and then some. So maybe okay, I can write this more explicitly. It is congruent to p, so I sum up all this once p times, and then plus p1 plus 2 plus and so on plus p minus 1 modulo p square, and this is you see that this sum is divisible by p, yeah, so this is equal to p modulo p square. Yeah, so so the conclusion that this is yeah, so this is y times zeta, because this is simply xi to the p, and not y. So this is contradiction, yeah, because we assume that our sigma is of order p. This is a contradiction. Okay. So we have so far we have checked that
Where do we get the contradiction?
because this is you see that this is sigma to the p, and we assume that sigma is of order p. So this is one. This should be identity, and we get a multiple of y when.
Okay, thanks.
Okay, so we have shown that no elements of odd order different from characteristic can appear. Now if characteristic is if characteristic of f is not 2, f the fixed field contains square root of -1, and sigma is of order 2, then f you see it's sigma is of order 2, so it is f is a quadratic extension of the fixed field. So denote the primitive element by x square for some x in f. X square because we can because of Kummer extension, we assume that the characteristic is non-zero, so we can
Можно все-таки вернуться назад немножко? Там why is the contradiction?
Куда?
Ну вот буквально предыдущее рассуждение. Почему, в чем проблема? Почему
В
противоречие?
смысле?
В том, что у нас
Здесь
на y сигма в p действует как умножение на единицу.
Сигма элемент p-того порядка, да, то есть сигма в p-той степени это тождественный автоморфизм, правильно?
Да.
Вот, мы действуем, сигма в степени p действует на y. Вот мы как-то все преобразуем, получаем y умножить на z, а z это нетривиальный корень из единицы. Главное, что нетривиальный, то есть получаем не y. А сигма в степени p это тождественное отображение. То есть тождественное отображение, мы подействовали на y тождественным отображением,
Да,
получили...
поняла, спасибо. А почему дальше мы пришли к сигма порядка 2? То есть здесь, по идее, должно как-то было быть использовано, что сигма имеет порядок больше 2, и я не вижу где.
Да, вот здесь, вот сумма 1, сумма
спасибо.
1 плюс 2 плюс p минус 1. Иначе будет просто 1. То есть там не будет противоречия. 2 плюс 2 это 0 по модулю 4.
Спасибо.
Вот, а сейчас мы делаем тоже. Now we do the same thing as on the previous step, but for p equals to 2. You see? So yeah, for some x, yeah. So for some x such that. So again, it is a Kummer extension. So x to the fourth is is fixed by sigma. Such that, yeah. So sigma x sigma x is some square root you see it is fixed. The fourth power is fixed by sigma. So sigma x is x times certain square root of -1. Okay, and therefore sigma square of x is square root -1 times square root of -1 x times x to its minus x. And this is again a contradiction because this is 1. You see? For the same reason, because sigma square should be identity, but it is not. Okay, next step. Now we take sigma and tau, just non-trivial elements in our group. Sorry.
Excuse me, and sigma and theta and tau are from
Just some elements, some non-trivial elements.
Thanks.
Yeah, some non-trivial elements. Sorry. Oh, I'm sorry. Maybe. Well, I have to rush. Yeah. So suppose that sigma of minus.
So,
Yeah.
okay, we're a bit over time, so let's then finish this proof and then do something
Yeah.
about it.
Okay. Yeah. Yeah. So. Okay. So they are non-trivial. Yeah. So we have so sigma tau as well as tau sigma and tau change the sign of square root of -1, and therefore they are, well, in a sense their ratio, so their ratio fixes square root of -1, so and therefore and therefore therefore this is simply you see that if they are non-trivial they should change the sign of square root of -1, but they are not, so this means that they are the same. So this shows that that only two elements can be in such a group, and finally the white is totally ordered. So FH finally FH is totally ordered when H is non-trivial. Non-trivial means that's of order 2. Namely, we say that x is greater than or equal to then y if x minus y is a square in the fixed field. Okay. And well, it is easy to check that this is correct because, for instance, if x is non-zero, and x is equal to t square in fh, then minus x is not square, because then well is not a square, yeah, because we don't have a square root of minus 1 in the fixed field. Is not a square, as square root of minus 1 is not fixed by h. Okay, and so this is yeah, and also either, so at least one of them, so at least one of them is a square, because yeah, at least so either x or minus x is a square. And that's it. Okay, so if you have some quick questions, then I would be glad to answer, but otherwise I will leave you. Do you?
No questions.
Have any questions? Well,
Okay,
it seems
so
like no.
all right, so see you on Wednesday.
Goodbye.
Thank you.
Ага, счастливо.
До свидания.
До свидания.